So do you have questions from your homework, the assignment, or from the notes, or anything like that that you need me to address before we continue on into Module 2 tonight? Okay, okay, that's neat. All right. So tonight, let me share my screen and kind of tell you where we are, and then I want to show you something too. Tonight, we're going to actually be beginning Module 2, and our focus at the beginning of Module 2 is going to be the normal distribution, which actually is a continuation of the probability distributions that we looked at last week. Last week, we looked at discrete probability distributions, and we looked at two types. We looked at kind of a generic or a general type discrete probability distribution, and then we looked at the binomial. We then began looking at continuous probability distributions, and we looked at uniform and exponential. Tonight, at the beginning of Module 2, we're going to continue discussing continuous probability distributions, and we're going to talk about one of the most powerful and one of the most useful in all of statistics, and that is the normal distribution. But before I get into that, Kaylee commented before we got started that she needed to take more notes, and that's probably a good idea, but I want to show you one of the things that I have been doing to try to help you as well that you may not be aware of is that if you go into the course, under the content, in the Zoom recordings folder, right now we're under Module 1, I have, for example, that my handwritten notes that I do on the computer. I started saving those and post them to the folder so that you could either go back through and fill in your notes that you took during class if you missed something, or if you have the capability and want to do so, you could actually print these off. Okay, so those notes are available. I try to label them with the date, and then it'll say notes, and they're in a Word document format, and then you have the corresponding video that goes with it. Okay, so like last week we covered the binomial and continuous probability, and again the notes are there. I did notice something, and so I will try to avoid from doing that anymore until I can figure out why it's doing it. But I did notice as I was glancing back through these that when I'm using the highlighter, which I thought would highlight, it's actually covering it up. So I do apologize for that. I didn't know that my tablet was doing that, but I'll try to make sure not to use the highlighter during the lecture so we won't cover up things. But those are available for you to either go back through and update your handwritten notes, or again, if you have the ability to print, you can print them. The other thing that you can do that might be of benefit as you're taking notes is these PowerPoints that we use during our discussions. are available in D2L. And again, let me show you where you might could find those. For example, the lesson tonight is the beginning of Module 2. So I would go to the Module 2 folder under the content, and we're going to talk about the normal distribution. And you have the PowerPoint here, normal probability distribution and its uses. And so the PowerPoint is there. It's available basically 24/7 through D2L. And so again, you could print that document off. You can, if you're familiar with PowerPoint, you can print the slides, if you like, individually on a page. I can print, 2 slides per page, 3 slides per page, as many slides as, again, they get smaller, it may get hard to read, but you can also do an outline. And with an outline, I'm going to click on that for just a minute. The outline gives you kind of what's on each page. And so that wouldn't be nearly as many pages to print. Like, for example, if I go back for a second, this particular PowerPoint, I can tell, has, let's see, 25 slides. So if you were to print it individually, you would have 25 slides. If you print the outline, let's see if I can get it to, looks like it goes maybe to 7 pages. Let's see, there's 1. It's 9. So you go from 25 pages to 9 pages. And there is some space in there that you might could possibly take out. So again, that's 2 resources that you might want to utilize. Again, if you've got the outline, you can make notes, written notes, into the margins as we are discussing. So hopefully those that might help you. If you are needing to take more notes or want to take more notes, to have them available to use during our discussion, or even after our discussion when you go back to do your homeworks, do your mini projects, and prepare for the midterm exam. So any questions on that, again, before I jump into tonight's lesson? Okay, so I am using the PowerPoint that I just showed you was available in D2L. Okay, so I'm going to start the slideshow. So again, we're continuing our discussion of a continuous probability distribution and its uses. And we talked a little bit last week about what a probability distribution is. A probability distribution in general describes what should happen if everything works the way it's supposed to. If everything works perfectly, the probability distribution describes what probably will happen or could happen as opposed to what actually did happen. We talked earlier in the very beginning, probably the first night, about frequency distributions, or you talked about frequency distributions in Statistics 1401. And frequency distributions actually are the reality. They describe what actually happened. Whereas a probability distribution oftentimes is a theoretical model. We're basing it on probabilities that have been assigned to a particular event. And probability distributions are used in a significant number of fields. They're used in business, in insurance, and in other situations. Again, we assign a probability to a particular outcome, and then based on that, we evaluate the results. It can be used, and it's hung up on me again. I don't know why it does that. Let me get it unlocked. And then I'll share my screen again. Okay, so we see it a lot in business with things like a scenario analysis, determining what's the worst case scenario or the best case scenario or the likely scenario. Again, because we assign probabilities to the particular events that we're considering. Sales forecasting, looking at maybe what the sales have been over the last 5-year period or the last 10-year period in that same particular month or that same particular quarter, if you're looking maybe at a grouping of months, so that you can maybe predict what the sales are going to be. That can help in terms of supply and demand. Do you have enough items to sell? And that kind of thing. Risk evaluations, rates of returns, think about stocks, standardized test scores, lifespan of consumable items, like determining how long a light bulb's going to last or battery's going to last. Even the birth weights of babies are based on a probability distribution, and heights. So there's a lot of uses for a probability distribution. One of the most powerful and most useful in the world of statistics is the normal distribution, which is the one we're going to focus on tonight. So thinking about the characteristics of the normal distribution. Again, the normal distribution is one that you would have studied extensively in Stat 1401 in the first statistics course. Although for some of you that may have been a while ago. So we're going to review that, but let me kind of give you a picture in case you don't realize what I'm talking about when I'm talking about a normal distribution. Normally, when you see a normal distribution drawn, you'll see a horizontal number line, and you have what many people refer to as the bell-shaped curve that is symmetric, and the value in the middle is the mean. If you'll recall, the mean is a measure of center. And there are several important characteristics of the normal probability distribution. First of all, it is continuous, which I already mentioned. It was a continuous probability distribution. Continuous means that I can draw the entire graph, that entire curve, without having to lift my pencil. There are no holes, there's no gaps, there's no breaks. It's continuous. It's a smooth curve. It is symmetric. The idea of being symmetric means that if you could imagine dividing this in half with this dotted line and folding it, you could not tell the left side from the right side. The left and the right are like mirror images. And again, that line of symmetry, or that imaginary line that I've drawn there, occurs at the value for the mean. We learned earlier or in the previous course that any graph that is symmetric, the mean, the median, and the mode are all virtually the same value. We focus on the mean because the mean uses all of the data values in its calculations. And so it's the best of the three options. There's only one mode, meaning there's only one value that occurs the most. And in terms of the picture, that mode would be typically at the peak. Okay, because that would show the value that occurred the most. Again, I mentioned to you that the mean, the median, and the mode, which are all measures of center, are approximately the same value. And again, we use or label that center point with the mean because the mean uses all of the data values in the calculation. And we often use the mean for other statistical formulas as well. So it is the best of those three. I also mentioned that the curve or the normal distribution is sometimes referred to as the bell curve. So it has a bell shape, again, where a lot of the values are kind of distributed or clumped together in the middle, and then it tapers off evenly in both directions. You have very few. Probably something you could relate to with the bell-shaped or the normal distribution is the idea of grading on the curve. If you've ever heard a professor talk about grading on the curve, they're trying to get this nice bell shape so that they have in the middle, they have a high number of C's, or most of the folks earn C's. A reasonable amount earn B's or D's, but they have very few A's and very few F's. So that's the idea of kind of this normal bell-shaped distribution is used in that idea of grading on the curve. The shape of that continuous symmetric bell-shaped curve is determined by two different population parameters. There are two numbers that kind of control the shape. Those two numbers are the population mean and the population standard deviation. And we can actually choose any number that we can think of for the population mean. We could have any number in our number system. And for the population standard deviation, we can have any number except 0. And so if you think about it, if I can have any number that I can think of for the population mean and any number for the population standard deviation in any combination, there are an infinite number of normal distributions. And I wanted to show that to you. So on the next slide, I have some examples. You have the green curve and you have the key over here to the side. But on this green curve, you have a mean of 2.5 and a standard deviation of 2. But notice how it still has that bell shape. I could imagine, again, if I draw an imaginary line through the peak, if I could draw straight, and I folded the graph across that dotted line, the left and the right appear to be the same, but it's kind of tall and skinny, but it still meets the criteria to be a normal distribution. It's continuous, it's symmetric, it's bell-shaped. Granted, it's a long skinny bell or a tall skinny bell, but it's still bell-shaped. Similarly with the red one, we have a mean of 0 and a standard deviation of 1. Again, if you focus just on it, again, hopefully you can kind of see that bell shape. Again, the idea is that it's symmetric and it's continuous. Similarly with the blue, you know what? They've got the blue and the green reversed. Sorry about that. They've got the blue and the green reversed. I didn't make the key, but they've got them reversed. But anyways, the blue one, again, if you look at it, you have it in the center. It does have a bell shape, but in this case, it's kind of a flat or a fat bell, if you will. Okay. So we can have any value for the mean that we can possibly think of, and any value we can possibly think of for the standard deviation except 0 in any combination. So there are an infinite number of probability distributions. And in a minute, we're going to talk a little bit more about that. But prior to the advent of technology, having an infinite number of normal distributions was a problem. It's not so much a problem for us today because we have technology that's going to help us. But there are a couple more characteristics that I want to address. Okay, so far, we've said the normal distribution is continuous, it's symmetric, it's bell-shaped, but the shape of that bell, if you will, is determined by the population mean and the population standard deviation. The next characteristic, and this is one that you kind of may have to trust Miss Ralston on, is the total area under a normal distribution is equal to 1 or 100%. And it even says here, this may seem unusual since the curve itself never really touches that horizontal x-axis. And I could prove that to you, but it would require that we use calculus. The whole premise of calculus is based on determining the area under any shaped curve, not just a normal distribution. But the area between the horizontal number line and that continuous symmetric bell-shaped curve, regardless of how it's shaped, is 1. That relates back to our probability rules. Remember, we learned that all probabilities are between 0 and 1. Remember, we said that 0 means the event is impossible, that no way, no how is that particular thing going to occur, regardless of what you do. Probability of 1 or 100% means the event is certain, that it is going to occur regardless of what you do. There's nothing you can do to stop it. And the other thing we learned that was important, that's a carryover here, is that the sum of all the probabilities, if we looked at all the things that could happen, that they total to 1 or 100%. Again, because that implies something is going to happen. And so this idea that the area under the normal distribution is equal to 1 connects back to that particular property. We're looking at it more from a visual perspective rather than a numbers perspective. And again, that's kind of one of those things you're going to have to believe Miss Ralston, trust Miss Ralston, because to prove it to you, I'd have to do some calculus. Finally, and you may see this written in some of your quiz problems, some of your midterm problems. You might even see it written in the research when you're reading research articles. We have a shorthand that can be used that basically says X is a quantity to be measured that has a normal distribution with a population mean of mu and a population standard deviation of sigma. And we write it out this way. And that statement means that X, our variable X, approximates a normal distribution. Normal starts with letter N, that's why it's an N, with a population mean, mu, which is the first number in the parentheses, and a population standard deviation sigma. Now, I usually try to write it out in words for you, but again, if you have a different instructor at some point or you're reading research, you may see that shorthand notation. Okay, so those are our characteristics of a probability distribution. Okay, it is continuous, it is symmetric, it is bell-shaped. The shape is determined by two numbers, the population mean and the population standard deviation. The total area under the normal distribution is equal to 1. And then we have a shorthand notation. One of the other key things that comes out of this discussion that we actually saw last week with the uniform distribution is that the area under the curve corresponds to the probability. And we'll come back and revisit that in a minute. I want to kind of give you again several examples of where you could use a normal distribution when you're trying to model a particular event, perhaps. For example, if we were trying to think about the height of a population, most of the people in a population, if we were looking at maybe all of the males within the United States or all of the males across the world, okay, most people in that specific population are going to be what we would consider average height. So meaning you're going to have a bunch of people here in the middle. Okay, then as you move out from that center or that average, because remember the mean is in the middle, that's your average. As you move out from the mean, you have fewer people that are like tall or taller, maybe like your basketball players, you know, those really tall people. And then even as you continue to move out further, you have fewer and fewer and fewer that are extremely tall or on the other end, extremely short. The stock market. We all have seen and or heard about the rise and fall in the prices of shares in the stock market. And so if people understand or realize, if analysts realize that the distribution of how a stock performs is normal, then they can begin to predict what's going to happen with a particular stock over a period of time, because part of the theory behind the normal distribution is that virtually 99% of all of the data should be within 3 standard deviations. And so we can use that to begin to analyze the investment, whether it will be a good investment or a bad investment, and what the expected return might be. That's honestly what stock analysts are going to do, and that's how they decide which stocks you should invest in or not invest in. Even with the economy for a country, the income of a country lies in the hands of the politics and the government. It depends on how that money is distributed between the rich and the poor. We are well aware of the fact that the middle class population is a bit higher. You have more people kind of in the middle that are average than you do people that are super rich or people that are super, super poor. And so again, if you look at the wages of that middle class, where you have most of your people, you get, again, a bell-shaped curve. And that bell-shaped curve has changed over time. The median or the middle income, the mean income, has increased from what it was, say, in 1970 to what it was in 2006 on this particular figure. So again, you can begin to determine that. And so if you're trying to maintain a bell-shaped curve, maybe that's when you think about raising the cost of living, or you think about raising the minimum wage. Related to healthcare management, think about birth weights. Typically, the birth weight of an infant is from 2.5 to 3.5 grams. Most babies are born within the normal range, but again, occasionally you'll have one that is significantly higher than another. For example, my daughter was born and she was 6 pounds 6 ounces. I'm not sure what that is in grams, but she was 6 pounds 6 ounces. Our neighbor that lived behind us at the time gave birth a week later, and her daughter weighed 10 pounds. So see, again, you have a lot of them are going to fall into that kind of what is considered a normal weight. And then occasionally you get some that are premature and are very, very small, or you have those that are born that are significantly larger. Inventory forecasting. It's a business strategy to kind of get a sense of what you need, what you have, what you need, when you need it. Again, using that idea of the demand and what's going to happen in the future, you can begin to plan for gathering products and services. I would assume that's something that you could use perhaps in operations management, again, with inventory forecasting. Blood pressure. Again, diastolic blood pressures are typically normally distributed. This is for men. This particular graph shows for men. Milk production of cows. You're going to have some cows, most cows are going to produce an average amount. You're going to have some cows that produce a lot more or a lot less. Hopefully you only have maybe 1 or 2 that don't produce very much milk, especially if that's what you're basing your career on if you're raising cattle and making milk. Temperature, if you look at temperature changes over a period of time, again, they follow from, the different seasons. They tend to follow a normal distribution. So again, there are a variety of applications for the normal distribution. It is one of the most used probability distributions in the world of statistics. The binomial that we talked about last week, we can actually use the normal to approximate the binomial. We can use the normal to approximate the exponential. There are procedures for doing that. So even if we couldn't actually do a binomial distribution, we can get a very reasonable estimate relying on the normal distribution. Now, we're not doing that in this course, but just want you to be aware of that. If I haven't mentioned previously, you can actually take an entire course on discrete probability distributions, and you can take a different entire course on continuous probability distributions. Okay, so we're again just kind of skimming the surface and looking at some of the ones that are used most often or ones that are useful in the world of logistics and supply chain or healthcare management. So I mentioned to you earlier that prior to the advent of technology, before computers, before calculators, the only way to solve a problem that involved the normal distribution was through the use of an equation and some tedious, complicated calculus. The formula, we learned in algebra, not that you remember algebra or want to remember algebra, but in algebra, we learned that, say, for example, the formula f of x equals x squared is the graph of a U-shaped curve. You may have learned that something like x squared plus y squared equals 9 is the equation of a circle. Well, the equation of our continuous bell-shaped distribution that is symmetric is this wild and crazy looking thing here. And so one of the challenges that mathematicians, statisticians had was that they were having to do those tedious, complicated calculus calculations every single time they went to solve a problem. And so they said, we got to do something about this. And so they said, well, how about if we create a standard normal distribution, one that we can compare everything to? And they wanted to choose numbers that made the calculations easy or easier. And so they said, we're going to let the mean for the population be 0. So they said, okay, our mean is like the middle, so that's our 0 line. 0 is easy to calculate with. Then for the standard deviation, they couldn't pick 0 because, I don't know if you noticed that the population standard deviation is in the denominator of that fraction looking thing. And you can't have 0 in the denominator of a fraction. So they couldn't pick 0. So the next best thing was a 1. So they let the standard deviation be 1. And then they created a table So they didn't have to continually do the calculations. They created a table that you could use regardless of what the actual mean value was and the standard deviation, because we would use what was called the z-score, where you take your data value minus the mean and divide it by the standard deviation so that you put it into this standardized scale. And then they would read the table instead of having to do those crazy calculations. The challenge is, guys, and I'm going to click on this link for a minute. The challenge is when you look at a normal distribution, and that was the one in this book, I thought. Okay, it doesn't give it to me. Let's go standard z-score table. See, there's all sorts of standard z-score tables. And every book would have, a lot of times in the textbooks that I had when I was learning this, okay, they had these tables in the front of the book, but you had to understand how to read it. The way this one is set up, it reads the area to the left of your z-score. But if I happen to go over to this table reads from the center to the z-score. So you had to know how the table was set up so that you could read it properly. It was messy, it's clunky, and it took a long time. So thankfully for us, we have technology to do it. We really do not rely on the tables and the standardized normal distribution anymore. We have the technology, and the computer is programmed with this crazy formula, and it does the calculations, does all the calculus and tedious calculations behind the scenes a whole lot faster than you and I ever could. So we're going to be using Minitab to work these problems. I'm not showing you how to do it by hand. I'm not going to show you how to do it on a calculator. We are going to use Minitab. The problems themselves are presented in two different ways. But let me pause for a minute to see if you have any questions before we continue and get into some examples. Okay, the problems that you encounter in this class can really be kind of categorized into two categories. I refer to them as kind of a type 1, type 2. Not really the way they talk about it in statistics, but again, I try to help you make a distinction between them. So we're going to begin by thinking about type 1. And in type 1, in the scenario, somewhere you're probably going to see a phrase like find the area under the curve, or find the percentage, or find the probability that. Okay? So that's kind of the type 1. And then we'll come back in a few minutes and talk about type 2. But I want us to get into these examples here. Okay, I mentioned to you earlier, and again, we saw this last week, that probability corresponds to the area under the curve. So when you see that phrase, area under the curve, they're actually also asking you for the probability. They're just using different words. The questions related to the normal distribution are going to be probably 3 to 5 sentences in length. It is important that you read the entire scenario from beginning to end. And then you need to go back and write down the information that you're given. Specifically, you have to be given 3 things, really 4 things. Okay. One is you have to know that your variable is normally distributed. So just like it would tell us that the distribution, you had a uniform distribution or you had an exponential distribution, somewhere in the scenario, it should tell you that the variable is normally distributed. You have to know the population mean, which is represented by the Greek letter mu. You have to know the population. I'm going to put this word in here, the known, because Minitab calls it the known. The population standard deviation, which is sigma. And you need your, whoops, sorry about that. You need your X value of interest. Okay, so you have to know somewhere in the scenario, it's going to tell you those 4 things. It should tell you that your variable is normally distributed, your population mean, your population standard deviation, and your X value of interest. You also have to look for words like less than, you could have greater than, you could have between, you could have less than or greater than in the same sentence or the same statement. You have to pay attention to the words, guys. The details are super, super, super important, because these words here are going to help you know which scenario to choose in Minitab. And we'll talk about what those scenarios are in just a minute. In the middle of this slide, and let me see which slide this is. This is slide 12. In the middle of slide 12, you will find the keystrokes that you need for Minitab. Okay, there's your Minitab instructions, and we're going to walk through it together. Okay, remember, we're actually calculating the area under the curve, which corresponds to a probability. If it is a probability, remember all probability values must be between and including 1. Guys, your answer should never, ever be negative, and it should never, ever be greater than 1, because you're finding a probability or a percentage. Okay, so we're going to dive in. There are, again, this idea of these 4 scenarios here: less than, greater than, between, and so forth. So we're going to walk through each one of those scenarios. And I notice I've got a misspelled word here. Let me fix it. All right, so this question says, according to the ACT, or the American College Test, results from the 2022 ACT testing found that students had a mean score of 21.524 with a standard deviation of 2.419. Assuming that the scores are normally distributed, find the probability that a randomly selected student has a reading ACT score greater than 26. All right, let's look at this. First of all, in the second sentence, it says the scores are normally distributed. So I know they're normally distributed. Okay, so I'm going to make me some notes over here. Normally distributed. Check. If I go back to the first sentence, it said that the results showed they had a mean score of 21.524. It doesn't explicitly say population, but since it's results from the ACT, we have to assume they were using all the students. So my population mean which is mu, is 21.524. You may want highlighters or colored pencils to help you underline these things, with a standard deviation of 2.419. So my population standard deviation is sigma, which is 2.419. So far, so good. I need one more thing. The last thing I need, it says find the probability that my reading score is greater than 26. So my X value is 26. Now, Minitab calls this format a specified X value. Now, let's think about what this would look like if I were drawing a picture of this problem. What would it look like? I know that I have a normal distribution, so I have my horizontal number line. I have my bell-shaped curve, and we label it with the mean in the middle, and the mean is 21.524. Now, it's in the middle. Guys, I hope that it makes sense to you that numbers that are to the left are going to be less than the 21.524. And numbers to the right are going to be greater. I should have put greater, not right. Sorry. Are going to be greater than the 21.524. Think about it like a number line. The 21.524 is right smack dab in the middle. And so numbers below it are going to be smaller. Numbers above it are going to be greater. That's a standard number line setup. It ain't changed. My point of interest is 26. So 26 is going to be to the right of the mean because 26 is bigger than 21.524. And it specifically says I want to be greater than that. Well, values that are greater than 26 are going to be to the right. So I'm looking for, if I'm thinking about the probability as the area under the curve, I'm looking for this area, this red shaded region at the end of my curve on the right-hand side. That phrase greater than, when you're looking at greater than is what we call right tail. And the picture helps me to see that. It's right tail because greater than is to the right and it's at the end of the curve. Now, I don't have to have the picture to solve the problem, but I'm trying to let you see or visualize what is going on. So I'm now ready to take this information that I've gathered from the problem. Everything I need has been given to me. And I'm going out to Minitab. Again, the keystrokes that we're going to use in Minitab were on slide 12 of the PowerPoint. Okay, on slide 12, we go to calculate a probability distribution. I think, nope, I'm wrong. Sorry, my fault. We go to graph, probability distribution plot, click. We want to view the probability for one curve. View the probability for one curve. Click twice. I have to choose my distribution. Again, if I look at the drop down, Minitab will do a lot of different distributions. We are doing normal, which is the default, again, because it's one of the most powerful. I then need to enter the mean, which was 21.524. That was given to me in the problem. I then need to enter the population standard deviation, which is 2.419. Okay, so my population standard deviation is 2.419. I then go to options. I have a specified X value because they said greater than 26. So I have a specified X value. Because it's greater than, it is a right tail. So I'm going to select right tail. And then I enter the value that I was given, which was 26. I click OK. I click OK again. And I get this graph. And I'm going to take this graph over to my PowerPoint so we can talk about it. Oh, that's not what I wanted. Okay, so this tells us this is a distribution plot. It's normal with a mean of 21.524, standard deviation of 2.419. That's the exact information from the problem. It has drawn the normal distribution. It has in the middle my mean, 21.52. It has marked 26 on my number line and shaded that red region. What I need is this number that's kind of hanging out in space above the curve. It is 0.03213. I need to put the 0 in front. Okay. That is the value in decimal form for the area that's shaded in red. Okay, so that means the probability that a randomly selected student has a reading ACT score greater than 26 is 0.03213. So there's about a 3% chance. If I take that decimal and convert it to a percentage, you're looking at about 3%. So there's about a 3% chance that a student would score greater than 26. Not a real good chance. The other thing that I want to emphasize here is that this says a randomly selected student. So we're only considering one student. And I point that out because next week we're going to look at what if we're going to consider 5 students at the same time or 10 students. Tonight, we're only looking at 1. Okay, let's do another one. I have the same scenario. Okay, it again tells me it is normally distributed. Okay, so I still know it's normally distributed. That hasn't changed. It's the same scenario we just completed. It tells me that my mean is 21.524. I'm going to use the symbol for the population mean. I'll shorten it, pop mean. It tells me that my standard deviation is 2.419. So my standard deviation is 2.419. That hadn't changed. That's the population standard deviation. And then it says find the probability that a randomly selected student has a reading score less than 21.7. And it tells me that was Georgia's mean ACT score. But I'm really only worried about the value. So my X value is 21.7. So again, if we think about this in terms of a picture, I have my horizontal axis, my bell-shaped curve, my mean is in the middle, which is 21.524. My point of interest is 21.7, which is going to be just a little bit to the right of the mean because it's just a little bit bigger. And we want to be less than that. Less than would be to the left. So I'm looking for this red shaded region under the curve that's to the left of 21.7. Go into Minitab. Again, we go to Graph, Probability Distribution Plot. One curve, we want to view the probability. It is a normal distribution. We're told that in the problem. The mean is 21.524, told that in the problem. Standard deviation is 2.419, told that in the problem. Options. Again, we have a specified X value, but this time it is less than, and I did fail to tell you that or point that out. Notice that less than, that the area is to the left and it runs out to the end of the curve. So this is called a left tail. Less than is a left tail. Sorry that I forgot that. Okay, so we want left tail. I'm going to select it. I put in my X value, which was 21.7. I click OK. I click OK again. And again, I get the graph. Now the numbers here on the X-axis do get a little jumbled, but I don't necessarily need them because what I'm looking for is the area, this red shaded region, which is this value that's kind of hanging out in space. Okay, so it is 0.529. So if we write our sentence, and you're not required to write a sentence, really, I'm mainly looking for this value, but so that you understand the explanation, it is the probability that a randomly selected student has a reading ACT score less than 21.7 is 0.5290. Again, that's in decimal form. If we put it as a percentage, it's about a 53% chance. Guys, all of the information that you need to solve the problem is given. The primary decision you have to make is it greater than, which is the right tail? Is it less than, which is a left tail? The third option is it could be a between. Again, it's the same scenario we have here, okay? Normally distributed. I keep writing this out to try to emphasize it for you. The mean is 21.524. the standard deviation is 2.419. And then it says find the probability that a randomly selected student has a reading score between 18 and 24. Okay, so in this case, I actually have two X values, and we usually use subscripts. The first one should be the lowest, which in this case is 18. And the second one should be the highest. You do not need to reverse them because it will calculate it incorrectly. We always work low to high. So you actually have 2 points of interest here because you want to be between those two numbers. Visually, again, if we think about it, you have your number line, your bell-shaped curve. The mean is in the middle, which is 21.524. In this case, I have two different X values. I have 18, which is going to be on the left, and I have 24, which is going to be on the right, and I want to be between them. It's like a sandwich. Okay, I'm in between those two numbers. Minitab calls the between middle because it's like you're in the middle of the graph. It's not a middle tail because I'm not at the end. I'm in the middle of the graph. I have everything I need. I'm going out to Minitab. Graph, probability distribution plot, view probability. It is normal. Mean is 21.524. Standard deviation is 2.419. Then we go to options. We have middle. And you have to give it the two values. Again, the first value is the smallest, which is 18. The second value is the highest, which is 24. I click OK. I click OK again, and I get the graph. Again, you can see things here on the number line. You can see where 18 is located, where 24 is located, and we're looking for the red shaded region. Again, the number kind of hangs out in space. It is 0.7744. So I would have the probability that a randomly selected student has a reading ACT score between 18 and 24 is 0.7744. Again, if we convert that to a percentage, it would be about 77%. So we've done 3 examples. You have a right tail, which is usually referenced by the words greater than. You have a left tail using the words less than. You have middle, which is use the word between. The last scenario and I want to make one up. So hold on. So we can use this same numbers. Okay. That might say something like less than 20 or greater than 23. Okay, so I could have a question like that. Again, it's the same question we just had, and I'm going to put this as example 4, and I'm also going to make a note that this is a special case. Okay, again, the question tells us that it is normally distributed. It's the same question that we've been doing. It tells us that the mean is 21.524. The standard deviation is 2.419. And then the question says, find the reading score that is less than 20 or greater than 21. So we have two conditions. Okay, we have two conditions. And I'm just going to tell you outright, Minitab does not calculate this directly. Okay, all the others we've been able to put the information in and get the answer out. This one with the two conditions requires a little bit more work. Now there's a couple of ways to do it. I don't know that one is better than the other. Okay, but I'm going to try to show it to you. Okay, so we have our normal distribution, bell-shaped curve, mean in the middle. And my conditions are that I want to be less than 20 or I want to be greater than 23. Now, Minitab does have another option that kind of looks like this picture. But Minitab makes an assumption that you have the same amount in each tail. And I don't know that. So I can't use that option. Okay, so I'm going to make a little note here. Do not use equal tails. We will never, ever use that option in this course. Okay, so this picture looks a little different. I want to show you what we're going to do, and then I'll have to provide a little bit more explanation. We're actually going to use the middle again. Because I can have Minitab calculate this middle that's between in this case 20, and 23. So my x1 is 20 and my x2 is 23. Okay, so I'm going to go out and do that, and then we'll talk about it just a little bit more. Graph, probability distribution plot, view probability. It's normal, mean of 21.524, standard deviation of 2.419, options. Again, I'm going to use middle, and I'm between 20 and 23. And I click OK twice. Now you're going to notice that the graph that Minitab created does not look like the one I drew. Okay, because what we did, again, we had Minitab calculate the middle, when what I really want or what I really need is this area out here in the end. Well, guys, think about this. If you think about that curve, kind of like a pan of brownies, and you hate the crust, so you're going to go in the middle and eat the brownies in the middle and not eat the crust. So I've taken the middle out. I'm going to take this out, and whatever's left is what I want. So remember, we know that this entire curve is 1. So we do 1 minus the middle. Okay, it's a special case. It cannot be calculated directly. You have to do this extra calculation using your calculator. Okay, so I have 1 whole, which is the entire curve, minus the middle, which is 0.4648. Notice this number right up here at the top. And I'm going to take that out. I'm going to use my handheld calculator. So I have 1 minus 0.4648, which is 0.5352. 0.5352 corresponds to my want need areas. So the probability that a randomly selected student would have a reading ACT score less than 20 or greater than 23 is about 54%. If you see the or, it is the special case. You have to do it this way. Well, you don't have to do it this way, but it's probably the most direct way. I'm not going to demonstrate it, but I will tell you the other option is you can figure the left and figure the right and add them together. You could do left tail plus right tail. You'd still come up with the same answer as me. Okay, but I'm not going to demonstrate that. Now, there are 2 other examples here. You can maybe look at those on your own because we only have about 30 minutes left and I want to get to type 2. Type 2, we get into what's called the inverse normal distribution. The question is worded differently because you begin by knowing the probability or the percentage, and you're trying to find the X value. So in thinking about these problems, and I don't think it's on the next slide, so I'm going to write it here on this one. With these problems, you're still going to know somewhere in the problem it's going to tell you that the variable is normally distributed. You're still going to be told or given the population mean. You're still going to be told or given the population standard deviation, which is sigma. But the difference is this time you have the probability, which could be stated as a decimal, or a percentage. You do not know the X value. That's what you're looking for. So the phrasing of the question is going to help determine which type of problem you have, which affects your choices in Minitab. I believe the instructions for the inverse normal are on slide 20. And again, you still have to think about whether you have a right tail, which is greater than, a left tail, which is less than, a between, or the outside, which is the or statement. I will tell you that primarily for these type problems in this course, I kind of tend to stick with right tail, left tail. Now, in the real world, that might not be the case. Okay. So let's take a look at an example. This problem says it's the same problem that we've been looking at. According to the American College Test, results from the 2022 ACT testing found that students had a mean score of 21.524 with a standard deviation of 2.49 and that the scores were normally distributed. Find the 80th percentile. So again, for emphasis, it clearly tells us in the problem that it is normally distributed. It tells us in the problem that the mean is 21.524. It tells us in the problem that the standard deviation is 2.49. What is different here is that it wants us to find, let me do a different color, wants us to find the 80th percentile. Now, you may not remember how to interpret a percentile. So let me review that real quick. A percentile is the percentage of the data that is below or less than the X value. Okay. Anytime you are interpreting or thinking about a percentile, by definition, a percentile is the percentage of the data that is below or less than the X value, which means for us that the percentile is a left tail. Now, again, let's look at a picture. I have a bell-shaped curve. My mean is in the middle, which is 21.524. Remember, the mean is a measure of center. So if you work left to right on this curve, we start out on the left at 0%. When I get to the mean, I'm at 50%. And if you keep going out the other direction, eventually you get to 100%. Okay, so you have to think about where would 80% be. 80%, if 50% is at the mean, 80% is going to be somewhere past the mean. And I have 80% below that score, 80%, which is 0.80. If you don't remember to go from a percentage to a decimal, it's the 80 divided by 100. And I'm looking for the X value that corresponds to that. In Minitab, this particular type problem is called a specified probability. This time I know the probability or the percentage. I do not know the X. So the commands are a little bit different and the keystrokes are on slide 20. But I'm going out to Minitab. I still go graph, probability distribution, view probability. It is normal. Mean is 21.524. Standard deviation is 2.419. I go to options. This time I have a specified probability that is in the left tail. The percent or the probability in the tail is the 80, and it does have to be entered as a decimal. I then click OK. OK. Let me carry this over here. You may think, well, Miss Ralston, that graph looks kind of like the other one. It does, okay? But again, look at the information. The number up here in the space is the 0.8. That represents our probability. I actually told it that value. What you need is the value on the horizontal number line. You're looking for the X. You're looking for the X. My X is on the number line. Here it is. My X value is 23.56. So the 80th percentile is 23.56, which means 80% of all the ACT reading scores are below or to the left of 23.56. 80% of the people who took the test scored below 23.56. Okay, I want to look at a couple of other examples again of these type, and I'm going to change examples. Okay, I've run out of examples with the ACT, so we're going to change examples. This problem says the lengths of pregnancies are normally distributed. Okay, so I'm going to make notes as we go. It tells me that my distribution is normally distributed with a mean of 268 days. So the population mean for pregnancies is 268 days. With a standard deviation of 15 days. So my population standard deviation, which is sigma, is 15. It says, if we stipulate that a baby is premature if the length of the pregnancy is in the lowest 4%, find the length that separates premature babies from those who are not premature. Premature babies often require special care, and this result could be helpful to hospital administrators in planning that care. Okay, so we have 4%. So again, I'm going to convert that to a decimal first off. 4 divided by 100, which is 0.04. Let's see if we can think about what the picture would look like. I have a bell-shaped curve. My mean was in the middle. It's 268 days. Okay, remember this goes from 0%, the mean is 50%, up to 100%. The other thing you may want to think about is this goes from low or lowest to highest. It might be bottom to top. The adjective there is important. It says in the lowest 4%. So lowest is going to be here on the left. And in this region to the left of that cutoff is the 4%. So this would be my lowest 4%. And babies born prior to that number of days would be considered premature. So these would be my premature babies. And anything over here is not premature based on the definition that we have. Because I'm at the lowest, I'm on the low end. Notice that that region is on the left. So this is going to be a left tail. The picture helps you to see which one you need. I'm going to Minitab. Graph. probability distribution plot, view probability. It is normal. The mean was 268. The standard deviation was 15. I go to options. I have a specified probability that's on the left again, but it's only 4%. I click OK, and I click OK again. And I'm going to copy this. Whoops, wrong place. And we get this graph. So again, I can see I've got my bell-shaped curve. My mean is marked in the middle. The red shaded region is marked as 4%. What I'm looking for is this X value, 241.7. So premature babies that are born between the 241st and the 242nd day of the pregnancy would be considered premature. I probably would round down and say 241. Okay, so premature babies would be defined as those born prior to, okay, premature babies are those born before the 241st day of the pregnancy, based on the way this is defined. Okay, I'd like to do one more example, but do you have questions? Okay. This one says men's heights are normally distributed. So again, they're telling me that my variable is normally distributed with a mean of 69 inches. Okay, so my population mean, which is mu, is 69 inches. And a standard deviation of 2.8 inches. The standard casket has an inside length of 78 inches. Okay, in this problem, we need it later when we're interpreting this, but this is extra information. I don't necessarily need that statement to work the problem. It then says a manufacturer of caskets wants to reduce production cost by making smaller caskets. Instead of making them 78 inches, he wants to make them smaller. What inside length would fit all men except the tallest 1%? Okay, so my percentage here is 1%. Again, I'm going to convert that to a decimal. 1 divided by 100 is 0.01. So again, let's think about what this would look like. I have my horizontal number line, my bell-shaped curve with the mean in the middle, which is 69 inches. Again, remember this goes from 0%, 50% in the middle, 100% on the right. Again, if you're thinking about men's heights, you would be going from shortest to tallest. We want to make caskets that will fit all men except those in the tallest 1%. Okay, so tallest is going to be a right tail. Because again, if you're looking at this graph, we go from shortest to tallest. So it's going to be over here on the right-hand side. And we want to exclude that tallest 1%. That would be the men that we would exclude. They would have to special order. So again, because it's a tallest, we're on the high end, it's a right tail. So I'm going out to Minitab. Graph, probability distribution plot, view probability. It is normal. My mean is 69. My standard deviation was 2.8. Options, we have a specified probability. This time it's a right tail and it's 1%. I click OK. So again, you have your bell-shaped curve. Your mean is labeled in the middle. The 0.1%, you can kind of see that little red shaded region there. And we are looking for this X value, which is 75.51. So the manufacturer could change the length of his caskets from 78 inches to about 75.5 inches. And he would still, the caskets would still fit 99% of all men. And he's saving 2.5 inches. Now that may not sound like a lot if you're only looking at one casket. But guys, over time, when you're doing hundreds or thousands of caskets, 2.5 inches is going to add up and would eventually reduce his production cost. And you may occasionally have that special order where you need a longer casket. There are some additional examples here that you can work through, okay, if you want to do that. But do you have questions related to the normal distribution? Hopefully you may remember some of that from Stat 1401, but also hopefully what we've done tonight will help you. Okay, so just as a reminder, the only assignment you have due, let me share my screen again. The only assignment that you have due this weekend is quiz 4 on the normal distributions. Next week, we'll pick up with what's called the central limit theorem. and look at its applications. Okay, any questions before we go? All right, if not, we shall adjourn, and I will see you ladies next week.
Thank you very much.
You're very welcome.